Right, good morning and good afternoon. Welcome everybody to this week's GS seminar. This week, we're very happy to have Maximilian from University of Vienna, who is going to talk about this very nice and exciting topic, stability and instability of relativistic fluids in slowly expanding spacetimes. So Max, please take over.
Thank you very much for the kind introduction, Puska. As some of you might know, so Liam gave a talk here last week. He's also a student of David Feynman, and I think he talked about some stuff regarding the stability towards the past. And as you can see from my title, so I'm also talking about stability and instability, but in this case on relativistic fluids, and we're also going to be focused towards the future. So this is future stability. We're going to talk about stable models, shock formation, and these kind of things. Also, like if you have any questions at some point, feel free to stop me and just ask right away, or I'm also obviously happy to answer questions at the end. Yeah, as you said, my name is Maximilian Ofner, and I want to emphasize that this is joint work with David Feynman, who is my supervisor here in Vienna, but also Zoe Wyatt. Some of you might know her. She's in University of Cambridge and also co-supervising my PhD thesis. And there's Maciej Maliborski. He is our local Vienna numerical relativity expert, and Todd Olenek from Monash University. And all of the results that I'm going to talk about are mostly like papers in some combination of these people. Yeah. Okay, so let's get started. I'd like to give maybe a brief overview of what I'm going to talk about. So we're going to talk about mathematical cosmology. So I put a picture of the cosmic microwave background radiation here. So the first thing is like, okay, so we want to talk about mathematics and about cosmological fluids. So the question is, what are we even studying here? What are people interested in? And in particular, like what types of PDEs are we studying? So this will be the equations of motion for a perfect fluid in relativity and the Einstein equations, but we're going to look at this in more detail in just a second. I will kind of give you an idea of what some maybe interesting solutions to these PDEs are. I mean, there are obviously lots of other interesting solutions, but we are especially going to be interested in cosmological solutions, and in particular those which are like relevant maybe to lambda CDM or other interesting cosmological models. We're mostly going to be concerned with the stability and also instability of these models. So the question fundamentally is like, will our solutions or decay back to like a highly symmetric state, or will they kind of have some divergences and maybe form shocks or something like that? So that we're going to investigate. Something that I'm going to talk a bit about is the so-called linear regime. I'm going to introduce what that means exactly, but I can tell you right now, so this is not like linearized Einstein equations or something like this, but this is referring to the expansion rate of the universe, which is going to be a linear function of time. We're also going to talk about the decelerated regime, where we have some interesting, more recent results that I'm going to talk about in more detail. And yeah, so I think maybe the kind of the goal of my PhD thesis was to combine all of these results in a complete picture. And yeah, so I hope that I can give like an overview and convince you that this is interesting and that we are advancing and like categorizing all of these different things. So let me start off by reminding you a bit about what kind of system we're talking about. So I know, forgive me, most of you have probably seen these things many times, but I'm going to still go through them so that we're all on the same page. So the system of PDEs that we're going to study is the so-called Einstein-Euler system, which is written here. So first we have the Einstein equations. These are equations that relate the curvature of space-time to the matter content. So we have the Ricci tensor, the Ricci scalar on the left here, and also like a cosmological constant. And on the right-hand side, we have the energy momentum tensor. Most of the models that we are going to talk about will assume that lambda is equal to 0, but there's also like a lot of literature and important results that I'm going to mention in which lambda is positive, which is assumed to be true also by cosmological observations. And these equations, the Einstein equations that we can kind of think about in a way as like sourcing the evolution of the metric with matter, we can complement with the conservation of energy momentum, which is this equation. And in our case, this will be the relativistic Euler equations in some sense or another. So this is just that the energy momentum tensor is divergence free. And what we use usually in this context is this type of energy momentum tensor. So we have T is given by this expression. Rho in this case is the total energy density of the fluid. In relativity, usually we throw internal energy and the rest mass energy into one variable, which is rho. P is the pressure. U is going to be the fall velocity of the fluid. So if you assume that the space-time is filled with fluid, then at each event in space-time, each fluid element has a certain fall velocity that's given by U, right? And G is the metric. So we can write down these relativistic Euler equations, so to speak, and we can project them. We can project them onto U, and we can also do an orthogonal projection. And what we end up with are these two equations. Yeah. So if you know a bit about fluid dynamics and the Euler equations, compressible Euler, so you might recognize these equations. So they look kind of similar to the compressible Euler equation. So the first equation would correspond to, so this is like a kind of an evolution equation for the total energy density, right? And if you, in some sense, assume that the fluid would be incompressible, then this second term would vanish. And the second equation would be something like momentum balance, right? So these equations you can recognize from classical Euler. And something that I want to stress here is that, just not to confuse you, we will be talking about two different kinds of results, right? So we will be talking about results where we solve for this whole system. So we solve for the manifold, the metric, the energy density, and the velocity. And when we talk about problems like this, I will refer to this as the coupled Einstein-Euler system. But we can also just look at the relativistic Euler equation. So if we just fix a certain space-time, doesn't even need to be a solution to the Einstein's equation or whatever, we can still, on this background, study the relativistic Euler equation. So for example, on Minkowski background or something like that. Yes. And so this system is underdetermined that I've written here. And what we can do so that we have a closed system is we kind of have to prescribe a thermodynamic relation, right? So this is a compressible fluid. Thermodynamics plays a role. And what is usually done in cosmology is one chooses a so-called linear and barotropic equation of state. Linear is clear, so K, this is a fixed constant, yeah, ranges from 0 to 1/3 usually for the most popular models. And rho is the energy density. But what does barotropic mean in this context? So barotropic means different things depending on who you ask. But in the context of relativity, you usually mean that the pressure is a function of the total energy density alone. So if you would look at compressible Euler equations, you would also have a conservation of mass, and you also have conservation of mass in the relativistic setup. But this equation becomes redundant if you just assume that the pressure is a barotropic, is defined by a barotropic relation. I'm going to highlight two different cases. So if we set k to 0, this is usually referred to as dust. So this is matter that is just interacting gravitationally. For k is equal to 1/3, energy momentum tensor becomes trace-free, and we have so-called radiation fluid, and everything in between we will refer to as massive fluids. And you will see that these distinctions make all the difference in what I'm going to talk about. So let's discuss some solutions of the system, right? So we can assume by symmetry and so on, it makes sense to assume that we have a metric of this type. Yeah? So we assume that our metric is minus dt squared plus some factor a of t squared that only depends on time times some Riemannian metric. And this GM is a metric of constant curvature. So this could be, for example, like a hyperbolic space, could be a sphere, could be R3, so it could be flat as well. And it has constant curvature that I've written here as kappa. We will also, in a lot of cases, take compact quotients of these manifolds. This A of t is also very important, and it plays an important role in the way that we distinguish different cases. So keep that in mind. We refer to this usually as the scale factor. And now this linear expansion that I was talking about before comes into the picture. So we will say A of t is equal to t. Sorry, if A of t is equal to t, we will say that the expansion is linear. And I will give you 3 solutions to the whole coupled Euler-Einstein system or Einstein-Euler system that are of this type. So of course, like if we would like to find solutions of the whole system, then we also need a solution for the fluid. This means that we can plug this FLRW spacetimes into the Einstein equations, and then we will get a relation between the energy density and the expansion rate, so that we find explicit solutions of the Einstein-Euler system. So the first model I want to talk about is this is sometimes referred to as Einstein de Sitter. So in this case, I've assumed that the spatial curvature is 0, the cosmological constant is 0, and also the speed of sound is 0, okay? And this is a matter model, so rho is bigger than 0, but it's a dust model because the pressure is k times rho, and that's 0. And this is an example of, so this metric is an example of a decelerating model, because if you would take the second derivative here, then for all positive t, we would have a negative rate, right? So this is called decelerating. The next one is the so-called de Sitter model. You all know this. Spatial curvature is 0. And this is also a vacuum model, right? So the conservation of energy momentum is trivially satisfied, and lambda in this case is bigger than 0. And this metric is exponentially expanding, or like this, the spatial coefficient is exponentially expanding. We refer to this as accelerated, right? And in between, we also have a explicit solution to the Einstein's equations, which is, or to the Einstein-Euler system, that is, which is the Milne model. The Milne model is a model with negative spatial curvature. The cosmological constant is said to be 0, and also this is a vacuum model again. And this solves the Einstein-Euler system, obviously, for whatever equation of state you would like to choose. Okay. So let me say a bit about the heuristics of these models. So what do we know about the global well? Sorry?
Nothing. You're good. Yeah.
Okay, great. So let me maybe talk a bit about the stability of these fluid states. So let's assume we have these kind of states which are described by these highly symmetric models that we had before, right? So what happens if we perturb them in some suitable topology, right? So we could say, okay, we have our data. Our data is this symmetric state, and we assume that we have something that is closed in some Sobolev space. So what happens to the evolution of this data? And I drew a picture here. So and this is convenient because it already highlights what I'm going to summarize about the results in the next slide. For example, if you look at Minkowski space, if we have initially a slight perturbation of our data, and this can actually be arbitrarily small, but not the trivial state, and we let the fluid evolve over time, then we see that we will get steeper and steeper gradients. So you can think about problem of characteristics, where you would just have crossing of characteristics at some point in the future, no matter how small your data is, unless it's completely trivial. And the steepening of the gradient could, for example, be the gradient of the fluid velocity that would correspond to shock forming. Now, if we look at a model of exponential expansion, so for example, we perturb around the Zito space or some other FLRW solution, excuse me. We will see that in general, this is not the case, but something different happens. So if we have an initial perturbation of our data, we see that this data regularizes over time. And so we converge back to the original state of the fluid, which is this highly symmetric FLRW state. So you could say, okay, you have one model, which is an extreme, the Minkowski space, which has no expansion, and then you have an exponentially expanding model, which is another extremal case. So what happens in between? What happens for other rates? So we can say expansion stabilizes the fluid, as is written here, but the question is, what is a sufficient rate of expansion to stabilize the fluid? I'm going to go quickly through this list of research, preliminary research in this field. There's a lot of works, and I don't have time to go into everything in detail, but I took the liberty to just highlight some of them for educational purposes. So first, there's this huge book by Dimitrios Christodoulou, seminal work, which studies the relativistic Euler equations on Minkowski space. So in this case, you just take a fixed space-time Minkowski space, you let your fluid with some compactly supported perturbation evolve. And what he found in this result is that your solutions form shocks generically. And that will be true for almost any equation of state, unless you take something that is very arcane. But then there are these results. There's this result by Brauer, Randall, and Euler, which is in a Newtonian setting. And what they observed in this result from 1994 is that if your spatial background is expanding in a certain way, then this can, so to speak, drive the characteristics of the fluid apart and lead to regularization. So you don't have any shocks forming. So this was taken by several people as kind of inspiration to study the full relativistic problem. So there's, for example, this result by Igor Rodniansky and Jared Speck from 2013, where they looked at the complete coupled Euler-Einstein system. in the presence of a positive cosmological constant. So you would have an exponential expansion rate. And what they were able to show is that like massive fluids, so these are the ones between 0 and 1/3, are actually stable. And there's another result here by Jared Speck that I'm going to talk about in a bit more detail, in which he just looked at the relativistic Euler equations again, and he took his spacetime to lower expansion rates. So he looked at almost like linear expansion, or like just slightly above linear expansion. We're going to explore this in a little bit more detail in a second, but I just want to mention, again, this is not a comprehensive list. There are works by, for example, Mahir Hadžić, by Todd Olenek. There's work by Puska. There's work by Helmut Friedrich, by Juan Valiente-Krohn, and many others, and collaborators, and so on. So yeah, it's a rich field. But let's get back to this result by Jared Speck. So what he was able to show is that if our scale factor that we have in front satisfies certain integrability conditions, then this leads to stability in certain cases. So for example, the first thing here, no worries, I have a kind of like a sketch of this later on, so that you don't lose the big picture. So for k is equal to 0, which is dust, he was able to show that if 1 over the scale factor is square integrable, then this already leads to the fluid being stable. So that's a kind of very weak condition. So this means that like if your fluid expands faster than t to the 1/2, then it's already stable. Sorry, your background expands faster than that. And for radiation, he was able to show something similar, that if 1 over the expansion factor is integrable, then the fluid is stable. And this is also a sharp result. So he showed that if 1 over the scale factor is not integrable, then there's actually an instability. So what was not really answered in this paper is like what happens in between. So he did have some results on that, but these results do not include like the linear expansion line, but only everything that's faster than that. And also except for radiation, we don't really know what happens below these stable rates. So what happens between these stable thresholds and Minkowski space, for example. Okay, so let me just give you a picture now of these results so that we can kind of see this. You're going to see this plot a few more times. So I'm going to take a bit of time to explain it. So on the horizontal axis here, we have this parameter alpha. And as you can see, I've written the metric here. So we have minus dt squared plus t to the 2 alpha times gamma. So in this case, a of t, our scale factor, would be t to the alpha, right? So 1 corresponds to a linear expansion rate. Everything that is below 1 corresponds to a decelerated regime, above 1 accelerated regime. And here on the vertical axis, we have the speed of sound parameter. And we're also we're mostly going to be interested in the ranges between 0 and 1/3. So I've just plotted these here. And what is already in red here is the results of Christodoulou for Minkowski space. So we see that, so red in this case means that the fluid solutions are unstable. And we can now add the result by Jared Speck, which tells us that, okay, if we are in the regime of dust, so the x-axis, that is, everything that is faster than t to the 1/2 is stable, right? So because it's 1 over this is square integrable. And then for radiation, everything that is faster than t to the 1, so everything faster than linear expansion is actually stable, and below that it's unstable. And this is the range in between what I was referred to as massive fluids. But we don't know anything yet about this linear line, which I'm going to talk about now because it's a bit more difficult. Okay, so results in linear expansion. First of all, there was this result by David, Zoe, and Todd, in which they were able to show that these homogeneous fluid solutions, if we have them on a fixed background with linear expansion rate, right? So we have here just torus with the flat metric, and expansion rate is linear. Then massive fluids, so again, this is the range 0 to 1/3, are stable under irrotational perturbations. This is a bit of a more lenient setup because if you know about relativistic fluids, you know that if they're irrotational, your fluid kind of satisfies a sort of integrability condition, which means that you can find a potential, and all of the fluid coordinates are just described by derivatives of this potential. So you can put everything into one parameter, and this parameter satisfies a wave equation. So that's a bit of a nicer, easier way to treat this. And then there's the second result, which is a bit unrelated, but it's also in linear expansion. This is by David, Zoe, and myself, in which we were able to show that the Milne spacetime, so this is also linear expansion, negative spatial Einstein curvature, is a stable solution to the whole Einstein dust system. So this is a pretty technical and involved proof. And as I said before, so from the spec paper, we already knew that this was true for the fluid alone. But it is, in the case of dust, it's significantly more harder to do it in the full coupled problem. And then there's this third result from, again, David, Zoe, Todd, and myself from 2023 that I'm going to be talking about in a bit more detail. So this is, again, you take all four-dimensional FLRW models with compact spatial slices, negative spatial Einstein curvature. So this is essentially Milne, and these are stable under solutions to the Einstein-Euler system. And this is for the whole massive range. So this is a bit more complicated, and also, like if you look at this result from the fluid side, it's not so complicated because if you set the pressure to 0, which you do in dust, you have a decoupling of the evolution equation for the fluid velocity, right? So you can treat this independently. Makes it a bit more easy on the fluid side, but here the geometry is much more involved. But here, yeah, the fluid becomes very hard to understand. And I'm going to talk about this result in a bit more detail. So I don't want to bore you with a lot of technical details, but I'm going to try to give the key idea. And I want to also take a bit of time here to explain to you how, I mean, like all of these results that I showed here, this is very abstract, right? So how do you actually deal with these things when you actually have to compute things, and what are the structures that you use? What type of equations are we looking at here? So one of the key ideas of this last paper was that you could use a transformation. This is this transformation that I've written as A and B. So you transform your energy density rho and your fluid velocity u into some new set of fluid variables, which are here given by psi and small z. So you can think of psi as like your new energy density and small z as your new free velocity. And you can do it in a way such that some conditions are satisfied. So first of all, the relativistic Euler equations in these coordinates, they are a symmetric hyperbolic system. You can also put them in symmetric hyperbolic form in the coordinates rho and u, but it's kind of important that you can still do this here. So this brings a lot of computable things with it, right? So you know that, okay, so if you have some matrix A0 here, and you can symmetrize the system. So A0 would be like some matrix that can depend on the fluid variables, but is still positive everywhere. And in this case, these equations have a nice existence theory. So you would know that locally your solutions exist for sure, right? Yeah, just maybe let me explain here. So we have some coefficient matrix for the time derivative, and the derivatives here act on this capital Z, which is the solution vector essentially, right? So it's composed of psi and small z, and these matrices A0 and AK, they depend on the variable itself. So it's a quasi-linear, first order quasi-linear hyperbolic system. And the matrix CK is special, and you can kind of filter that out in a sense from the coefficient parts of the spatial derivatives. And this coefficient matrix CK is constant, which will be relevant in a second. One thing that this transformation does for us is that a lot of parts of these matrices, you don't really need to care too much about what these are, but like what it does for us is that we can control a lot of these, a lot of the elements of these matrices by z squared, right? So this is like the transformed fluid velocity, which will become clear in a second why that's useful, because this is essentially where all the decay of the equation is hidden. Now, as for this H, which is the inhomogeneity on the right-hand side, you can furthermore split this apart into these two vectors. So here you have minus times a positive constant, and that constant depends on the speed of sound parameter, right? So this is also a reason why this proof would not work for dust, for example, because in this case, this constant would be 0, times this solution vector, but only in the z direction, right? So you can see that, like, okay, in my evolution, I get back something negative on the right-hand side, but only in the velocity components. And then plus some error term that we can, again, control by c squared, or products of it with something else can be controlled by z squared or something like that. Yeah. And I want to guide you now through one of the essential calculations that you do with all of these problems. So all of these symmetric hyperbolic systems have kind of a natural energy functional attached to them. So this was already realized by people in the 50s and so on. So K.O. Friedrichs did some work on this. I think this is mostly attributed to him. And sometimes also this kind of approach that I'm showing you now is called a Friedrichs type estimate. Okay, so what happens, like, so this energy A0 is positive, right? So this is kind of coercive to some L2 norm of the solution. And right, so let's see what happens if we take the time derivative of this. Well, our time derivative will hit this first z and the second z, but as A is symmetric, we can just transpose, so we get 2 times this first part. And then we are left with an additional part here where the time derivative hits the A0 component, right? So now we just put in the equations of motion. So from partial tz here, we will get, sorry, from A0 partial tz, we will get the spatial derivatives. We will get this one beneficial term from the H term that I was talking about. So we will get something minus some constant times the L2 norm of small c squared, plus some error terms, plus again this time derivative of A0. And what we can do now is like for the first term, we can always integrate this by parts, right? So I don't know. I think was there a question? No. Okay. Okay, so we can integrate this by parts, and we have then this kind of prototypical term where we have like c squared, and then in between we have this 4 divergence of the coefficients. And when we put all of this together, we get a type of estimates like this, right? So we get something like minus c times the L2 norm squared of the velocity plus something of order of the like pointwise norm of z times, and then something of 0th order and 1st order, right? So this we can of course only get if we have like beneficial estimates on the C transpose F, this arrow term, and also on this divergence. So this is where a lot of the magic is hidden and what you have to find. And one thing that you would note here immediately is like, okay, you have a problem with regularity, but that's actually not a problem because the term that we have here in this estimate that gives you the derivative, which comes from this expression here, it will only be of that order regardless of what kind of energy you're trying to control. Because if you have a higher order energy, you will have derivatives on these C components here, but A0 will always stay the same. And if you perform your integration by parts, you will always have like the same coefficient here. So if you just go high enough with your regularity, at some point you will be able to absorb this term. So there's no issue with regularity at the end of the day. And yeah, obviously, like in some bootstrap regime, we can assume that this coefficient is then small and we can absorb everything. So we can show by this mechanism that our energy is bounded. Yeah, I wanted to talk to you about this and just quickly explain like what the general ideas of these estimates usually is. So I've mentioned these results again. So this by David, Todd, and Zoe, and myself, and so on. So what we've essentially done now is this. So we have cleared this linear expanding line. And we've not only done so for the fluid itself, but also for stability under the whole Einstein-Euler system. But the question that still remains, what happens in this region, right? So the decelerated region is completely open at this point. And it makes the problem way more difficult because you would have a lot of terms that usually would be integrable in time due to the time coefficients from your equations of motion, but they are not in this decelerated regime. Okay, so let me explain how you can prove something in this regime. Also, like something to mention here, you can see that there's a significant difference between radiation and dust, but it's not clear in this bulk region whether or not like there's a difference, whether a region is stable or unstable. That depends on the speed of sound. So it could be that everything is stable, everything is unstable up to this point or so. And interestingly enough, as we will see, there is a dependence on the speed of sound. So I've kind of written the system in a simplified way here, right? So this is in like 1+1 symmetry. You only look at one spatial coordinate, and I've written the equations of motion of my fluid in my favorite variables here. So this v is sort of like a x component of the velocity, and this L here is a sort of energy density. And what is immediately clear from this, and not unique to this problem, is that similarly to what we were discussing before, in the evolution equation for V, we have some natural decay-inducing term, right? So we have a minus some fixed constant depending on t, the velocity itself, but we lack such a mechanism for the energy density L. And this is going to become a problem because, as I said, some terms that would usually be integrable in the fast expansion models or even in the linear expanding models are not integrable anymore. So, for example, if you look at these coefficients here, right, you have this t to the minus alpha. In the accelerated regime, where alpha is bigger than 0, alpha is bigger than 1, these coefficients would be integrable, right? And then in the linearly expanding regime, they would you could treat them in this other way that I was describing kind of before. But here, all of these approaches fail, and what you have to do is like you have to kind of artificially take some of the decay that you have for the velocity term and translate it into the density term. And the way that you do this is by correcting your energy in this way. Okay, so what is written here? So the first two terms are kind of like the square of a homogeneous Sobolev norm of first order of the velocity. So you have velocity of the derivative of the velocity, and then the derivative of the energy density. But then we can also complement this here with another term. And you might look at this and think like, okay, so this is not coercive anymore, right? Because you have different regularity here. But that's not a problem because since we are on a compact domain here, we can control V in terms of its first derivative by using the Poincaré lemma. So, and also like this coefficient here decays sufficiently fast because alpha in our case is always smaller than 1. Right. So what does this energy now do for us, right? How does it get us anything good? If we look at the time evolution of this functional and we hit the velocity part here, we can see in the equations of motion of the velocity, we have a term here that includes the derivative of L, right? And it also has a negative sign in front of it. So if you assume that V is small and so on, like you will get a negative definite term of partial L squared, right? So this is very good because this way we can in addition to controlling the velocity part, we can also control the density part, at least at this order. But of course, what happens when you hit the other part? Well, something bad happens, right? So if we hit this spatial velocity of L, the spatial derivative of L here, with our time derivative, we will get a second derivative of the velocity. Now, we can integrate by parts, and so we get the derivative of the velocity squared here. But if we integrate by parts, we will get another minus here. So this will result in a bad term, right? That will take away from our decay. So we now have like an additional good term that looks like dx L squared, and an additional bad term with a positive sign and a partial x v squared. And what we can do now is we can just balance them out completely, like find the correct configuration so that you can go as low as possible with your expansion rate. And you find, if you do this, you'll find this kind of relation. So this means that if you pick your favorite speed of sound parameter k, I can give you a expansion rate for which, if the expansion rate of your universe is faster than this set expansion rate, then the fluid will be stable for this specific speed of sound. Now this is obviously not a sharp result because we haven't shown what happens at this point, and we also don't know anything below except for that it's unstable for Minkowski space. So what we did to supplement this was we did some numerical considerations actually. So let me show you a bit of what we found out, the kind of data we collected. So you can see two, I would say, prototypical examples of certain points. So on the left, we have in this parameter space, so this is, sorry, let me just go back for a second. So we're again in this K alpha range somewhere, right? And for the point on the left, alpha is equal to 0.7, K is equal to 1/6. And on the right, we have K is again 1/6, but the expansion is faster, alpha is 0.9. And we see like a characteristic difference between these, right? So on these plots, on the x-axis, we have the time, and on the y-axis, we have some norm that we decided was significant. And we can see that for different initial data sizes, so we have here initial data 2 to the minus 1, 2 to the minus 3, and so on, like different prefactors of initial data, we see that for this point in a slower expanding regime, we have blow up for each of these initial data, but you can see like the smaller you make your data, the more the blow up goes towards the future, but it will always happen. On the other hand side, we have this example in which we have a faster expansion rate, and we see that for larger data, we see again that the norm diverges after some short time interval. But if we go to smaller data, we see that the norms eventually decay and don't grow anymore. The problem with this idea is that if you get closer to a transition region between stable and unstable, your numerical simulations become more and more computationally intensive, and it becomes increasingly difficult to judge whether or not you're actually in one or the other regime. Because, I mean, you could be just bottlenecked by your computation length, like how much time you have, right? But what we did instead was we kind of did a scaling analysis. So if you look at this picture on the left, here we have the speed of sound parameter K is equal to 1/6. And here we have initial data size on the x-axis and the existence time on the y-axis. And we did this for several expansion rates. And what you can see is that, like in this log-log plot, you have kind of like a nice linear dependence between these two variables. So, for example, for 0.05 alpha, you see that the blow up happens pretty fast, right? And if you go to fast expanding regimes, you see that the blow up takes longer and longer and longer. And you can look at the slope of these curves, and you can, in principle, just say, okay, so is there a dependence between the slope of these curves and the expansion rates? I mean, we see that there's a dependence here, so the slope becomes steeper and steeper, the bigger the expansion rate. But you would expect that at some point, the slope of this curve would become infinite, so you would just have a vertical line in a sense. And if you would have a vertical line, this would mean that for small data, your perturbation is stable somehow, because the existence time would become infinite. So you can do this kind of scaling analysis, and you can find for different speed of sounds here, you can find a relation between this A. So A in this case is the slope of the previous picture, and the difference, or the logarithm of the difference of the expansion rate to some critical expansion rate. So you just have like a dependence 1/alpha star minus alpha. So and as you can see, these fit the model pretty well, right? And then you can numerically just try to find alpha star the supposed expansion rate where the system becomes stable for each of these points. So that's what we did. And now you might ask, okay, so we did this numerical analysis. We have this analytical proof for stability. So question is now, how do they match up, right? And as it turns out, they match up pretty well. So in this picture, you see again this parameter space, and the red dots are the unstable region, the blue squares are the stable region, and in between you have this gray curve. The gray curve is the lower limit of stability as predicted by this analytical argument that I was discussing before. And then these black dots are the stability-instability transition points that we get from the numerical analysis that I was talking about before. So yeah, needless to say, we were pretty happy when we saw that this matches up. But of course, it's not a proof, right? What we have proven, and not only in 1+1 dimension, but like in the full system, is that this region that is to the right of this line is stable. But we haven't proven anything rigorously about the unstable region. Also, one kind of curious point that I want to mention here is that dust is sort of special in this case. So if you remember the models from before, we saw that dust is stable all the way until t to the 1/2, not including t to the 1/2. So all of this line from 1 to 1/2 would be stable. But if you look at this region here, I hope that you can see this with my cursor here. So if you look at this region here, let's say you would have a family of initial data corresponding to a certain speed of sound parameter, and you would let this go to 0, right? Then you would have a family where all of these models would have a shock forming, but in the former limit of k going to 0, the shock would be completely avoided. So in that sense, it's very interesting when you have this transition from like these massive fluids or the range k0 to 1/3 up to the actual dust model, where somehow this completely degenerates. Right. I just want to mention additionally, so this is just a result for this bulk region here, right? So our numerics don't say anything about radiation or dust. But there's also, so there have been people working on this, right? So there was this result by Speck that I was talking about before, where he kind of took a result from Christodoulou and showed that it applied for radiation. So he was able to show that shocks form for expansion rates smaller than the linear expansion in the case of radiation. And there has been some work on dust by some Chinese colleagues, and also we have in our most recent preprint we have reproven both of these statements in a nice and constructive way. And I just want to mention this so that you know, like, so these boundary regions are not like they're not open, but like this is already understood. Right. So yeah, let me maybe say a few concluding remarks to this, or give a summary of what I was talking about. So we looked at the linear regime, right? And we were able to show that this linear regime, the solutions to the linear regime for the whole Einstein-Euler system are stable, except for radiation. So that was in some cases, that was known in the case of dust for just the Euler equations, but not for the complete system, and we showed it for the full range of massive fluids and dust. What I think is very interesting is that in these decelerated regions, the type of fluid that you consider actually matters. I mean, I would guess that it's expected, but it's pretty difficult to show that formally. Yeah, as I was talking about before, taking this formal limit of k going to 0 is problematic. So that's also interesting that dust really, in this sense, behaves fundamentally different than fluids with pressure. Yeah, as I said, this proof that I was talking about is also true for the whole system. So the stability proof works in the whole system. And yeah, we can, what I was talking about in the last slide, we can also show results for radiation and dust by setting up some characteristic considerations or finding a Riccardi type ODE that shows that along some characteristics we have a blow up of the gradient or something like that. So I hope that this was a nice overview of relativistic fluids in slowly expanding spacetimes, and yeah, I hope you found that interesting. Thank you for your attention.
Thank you, Max, for the great talk. Amazing. So if we have any questions from the audience, now is the time to unmute yourself and go ahead. Do you have any questions from the audience? Anybody? Max, maybe I'll ask a couple of questions if that's okay.
Sure, go ahead.
Yeah, so in the phase diagram that you've shown, that's actually very interesting. What is the equation of the phase boundary? This yeah, is that
the boundary?
Yeah, like go back, like the phase boundary in the yeah, this black dot. Yeah.
So it's actually so it was this relation that I described here. Right, so it's a relation between the speed of sound parameter k and the expansion rate. And yeah, you can see this is like a nonlinear relation.
Wait, this is like this bar is blocking my view. It's on the bottom of the slide, right?
Can you
yeah.
not see? Can you not
yeah.
see it?
Now I can see. Now I can see. Oh,
but
yeah.
is it on your end or on my end?
I think it was on my end. Yeah. Now
Okay.
Now I can see.
Okay.
Yeah. Sorry.
Yeah. Yeah. Interestingly enough, you get this condition by just considering this energy estimate, and it naturally pops out that this is the optimal way that you can do it, so that you can still have the sufficient decay for this energy density part. So you have this nonlinear relation between the speed of sound parameter
Right.
and the expansion rate, and this is then exactly what is here.
Wow. Yeah, this is amazing. So that thing, like that relation that you get, that is dictated by the decay in the analysis, right?
Yes.
And that you exactly what you see in the numerics as well.
Yeah, I mean that's kind of surprising. I mean, I would be careful, and as I mostly do analysis, I would take this with a grain of salt, because we haven't proven anything about this unstable regime here, but I'm still fairly confident that this is true. I mean, it seems to agree, at least to a high degree. You know?
Yes. Wow. That's amazing.
Also, something to note maybe at this point is like, so all of this that we have done here, right? This is without the back reaction of the gravity, right? So we just have a fixed background.
Right.
But there are also solutions of the complete Einstein-Euler system here, right? So there's, for example, this Einstein de Sitter solution that I was talking about that sits about here, right? In the dust regime.
Yes.
Then there's the radiation solution, and then like there's also a curve between those. And there's been some recent article on Archive by one of Todd Olenik's students, in which he was looking at this numerically, and it looks like also numerically these solutions to the Einstein equation at least are unstable, which you would expect from the fact that they seem to be unstable from the fluid side at least.
Right. Right, yeah. If it's unstable from the fluid side, gravity probably doesn't make it better. It probably makes it worse.
Yes, I mean, it's, I guess it would be a bit unreasonable to assume that the fluid would that the
Yes.
geometry would regularize it in some sense, but it could still happen, right?
Yeah.
Maybe you would have some counteracting mechanism from the equations of motion of the geometry when they are sourced by a term that's only big enough, right? So.
Yes. Are you talking about this article by this guy, Eliar Marshall or something? I saw a couple of days ago.
Yes, exactly.
Ah, okay, I see.
So you've seen it before. Okay, great.
Like, I think he posted like a couple of days ago, right? Yeah. It's a numerical study. Right. Amazing. Thanks, Max. Thanks so much for answering the questions. And
no worries. Thank you very much for having me.
Of course. Does anybody else have any more questions for Max? Okay, if not, then we're gonna